Hello everybody, we're getting ready to do lesson 7.3 part 1 of pre-calculus math classwork today. And in today's lesson you will have 10 points will go on your notebook sheet and 42 points here will go on your classwork sheet. Okay, so for today's bell work, teachers, students, today's bell work. Solve the inequality and graph the solution on a real number line. So for 103, do that. And then down here for 108, write the expression as a logarithm of a single quantity. So here that is. Put your responses in here, students. Teachers, give your students 5 minutes. Turn off your video, come back in 5 minutes. Okay, welcome back for your solutions for today's bell work. For our first one up here, our inequality, to solve that inequality, factor this down into two binomials, and then our critical numbers here will be 7 over 2, and then -5 will be your zeros up here, and then testing the three intervals. You can test your inequality here, -5, less than x, less than 7 over 2. That would be your graph here of this inequality here. And it'd be an imperfect inequality, so these are open. And then down here for our logarithm, when we combine this logarithm into a single quantity, using our rules of logarithms, when you add two logarithms, that means that you have a product here. So 3 times x, 1/4 log base 6, 3x. And then when you simplify that even further, you have log base 6, 3x to the 1/4 power. Moving on to our lesson today. Our first page is a notebook entry here, students. Row echelon form and back substitution. The method of elimination can be applied to a system of linear equations in more than two variables. When elimination is used to solve a system of linear equations, the goal is to rewrite the system in a form to which back substitution can be applied. To see how this works, consider the following two systems of linear equations. So systems of three linear equations in three variables. Our first system, it would be this one here. 3 variables, 3 equations. That'd be our first one, and then equivalent system in a row echelon form. So this would be our second system here. The equivalent system in a row echelon form. So when we have this row echelon form, the second system is said to be in row echelon form. Here's our second system, which means that it has a stair-step pattern with leading coefficients of 1, 1, and 1. After comparing the two systems, it should be clear that it is easier to solve the system in row echelon form using back substitution. Okay, well, let's try an example to show how this works. Using back substitution in row echelon form, solve the system of linear equations. So we have a system here, equation 1, 2, and 3. And from equation 3 down here, you know the value of z equals 2. To solve for y up here, substitute z equals 2 up here into equation 2 to obtain y plus 4 times 2 equals 7. And when we solve for y, we get y equals -1. So now we know z and we know y. Next, substitute y equals -1 and z equals 2 into equation 1 up here. And when you do that, you get this expression here. And what does that amount to? Well, let's see what that comes to. X equals 1. So we solve for x and we get x equals 1 from that back substitution. So here's our solution here for that system. X equals 1, y equals -1, and z equals 2, and which can be written as an ordered triple. Here is our ordered triple: 1, -1, and 2. Check this in the original system of equations. Okay, let's try one. Use back substitution to solve the system of linear equations. Here is our solution here. So equation 1, 2, and 3. We know what z equals 2. Back substitute z equals 2 into equation 2. So y, when we do that, y plus 2 times 2 equals 2. And we get y equals negative 2 up here. So now we know y and we know z. So we just plug that in up here. And we get 2x minus the negative 2 plus 5 times 2 equals 16. And we get x equals 2. So here is our ordered triple for this system here. Okay, page 4, Gaussian elimination. Two systems of equations are equivalent when they have the same solution set. To solve a system that is not in row echelon form, first convert it to an equivalent system that is in row echelon form by using one or more of the elementary row operations shown below. This process is called Gaussian elimination after the German mathematician Carl Friedrich Gauss. Okay, so row echelon. Elementary row operations for systems of equation. 1. Interchange two equation. That would be a row operation there. 2. Multiply one of the equations by a non-zero constant. And 3. Add a multiple of one equation to another equation. So these are 3 types of operations that can be used to solve a system of equations. Let's try one example 2, using Gaussian elimination to solve a system. Solve the system of linear equations. So here's our system here. What do we do with that? Because the leading coefficient of the first equation is 1, you can begin by saving the x at the upper left and eliminating the other x terms from the first column. So we need to get rid of this, we need to get rid of that. So add the first equation to the second equation, produces a new second equation. When we add this to that, that goes away. And we add these two, we add those to equation 2. We end up with y plus 4z equals 7 now for the second equation. So now what do we do? Well, adding negative 2 times the first, we multiply this by negative 2 times first to the third. So we multiply that together. So negative 2 times the first to the third. This becomes negative 2x, negative, well actually 4y to minus 5y. That's your negative y. And then negative 2, that'd be negative 6z plus 5z would be negative z. And then negative 2 would be negative 18, and 17 would be negative 1. So that's how you get this here, this third equation, is by adding negative 2 times first equation to the third. Now that all but the first x have been eliminated up here, from the first column, go to work on the second column. Here's your second column here. You need to eliminate the y from the third equation. We need to get rid of this y here. So how do we do that? Adding the second equation. We're just going to add our second equation to the third equation. This goes away. We add 4z to z. That equals 3z. And then 7 to negative 1 would be 6. So here is our stair step. Okay, so moving right along here. Here is our triple that we left from the previous page. Finally, you need a coefficient of 1 for z down here. This needs to be changed to 1 in the third equation. So what we do, we multiply through by 1/3 here, multiply this row here by 1/3, and we get z equals 2 now for our third row there. So this is the same system that was solved in example 1. As in that example, you can conclude that the solution is x equals 1, y equals negative 1, and z equals 2. And so what would that look like as an ordered triple? It would be this 1, negative 1, and 2. That would be your ordered triple. So let's try one now. Solve the system of linear equations and check any solution algebraically. So we have this system here. So equation 1, equation 2, equation 3, let's label that so we can kind of identify what we're doing here. So x plus y plus z equals 6. So we're going to multiply negative 2 times equation 1 plus equation 2. And this is what we get here. We end up with negative 3y minus z equals negative 9. We multiply equation 2 by negative 2. And then for here, we get negative 3 times equation 1 plus equation 3. So we multiply equation 1 by negative 3, and then we just add it to equation 3, or row 3, and we end up with this. So here's step 1 here. Then step 2 is now for our third, we want to go in row echelon, so we have to get rid of this one out here. So negative 1 times equation 2 plus equation 3. So negative 1 times equation 2 plus equation 3, and we end up with this, negative 3z equals negative 9 down here. So one more step here, or we could just go from here. So we get negative 3z equals negative 9, z equals 3. We plug that back in, we back substitute now. Negative 3y minus 3 equals negative 9, therefore y equals 2 in this situation here. Back substituting further, we get x plus 2 plus 3 equals 6, x equals 1. So here's our ordered triple for this system here. Okay, page 10. The next example involves an inconsistent system. In other words, one that has no solution. In order to isolate one variable, so it has no solution, so we need to isolate one variable. You can then solve for the value of the variable and use back substitution to find the values of the remaining variables. The next example involves an inconsistent system, one that has no solution. The key to recognizing an inconsistent system is that at some stage in the elimination process, you obtain a false statement, such as 0 equals negative 2. So when you're trying to solve these systems, and you end up with something like this, a false statement, that's a dead giveaway that it is an inconsistent system when you end up with something like that. So beware of that. So let's try one now, see what it looks like. An inconsistent system, solve the system of linear equations. Here's our system here. So adding negative 2 times the first equation to the second equation produces a new second equation. So we get a 0 here in row 2 here. 5y minus 4z equals 0. So adding negative 1 times the first equation to the third equation produces a new third. So we have a new third here. So we have a situation here, don't we? 5y minus 4z equals 0, and 5y minus 4z equals negative 2. That's a little suspect. So when we get something like that, adding negative 1 times the second equation to the third equation produces a new third. So now we have 0 equals negative 2. So that is definitely a dead giveaway there. Because 0 equals negative 2 is a false statement, you can conclude that this system is inconsistent, so it has no solution. Moreover, because this system is equivalent to the original system, you can conclude that the original system also has no solution. Well, let's try one now. Solve this system of linear equations and check any solution algebraically. Here's our system here. So equation 1, equation 2, equation 3, we're going to interchange. We're going to interchange equations 1 and 2. We're going to put that one up here, and then this is going to go down there. So now we have x plus y minus 2 equals 3, 3z equals 3, and then negative 3 times equation 1 plus equation 2. So we're going to combine negative 3 times equation 1 plus equation 2. We get this, And then -2 times equation 1 plus equation 3, and we end up with this. So now we have this situation here. We have the same quantity equaling -8 here, and then also +2. That's definitely suspect. And to go further with it, so a negative of equation 2 plus equation 3. So when we add these two, we get 0 equals -10. And that don't look right, does it? Inconsistent, no solution. So that's when you know that you have a inconsistent system. And that is 7.3 part 1, pre-calculus math. If you need a solution PowerPoint, class worksheets, homework sheets, or anything else, here's my email. Thank you very much.